Hello. So we learned this basic structure. This is an example for fixed cost and marginal cost example, but we may generalize this idea like to other examples. For example, demand function or supply function can be estimated using a linear regression model. So remember, demand or supply function is to explain the quantity produced or quantity demanded as a function of price. So if price increases, there will be less demand or there will be more supply. So as price changes, the output is the quantity. So quantity is on the left hand side and price is on the right hand side. There is an error and there are two parameters. In this example, what's particularly important is beta 1. So when price increases like by $1, how much the quantity would increase or decrease, right? That is beta 1. So we call beta 1, the parameter beta 1, as the elasticity of demand, elasticity of supply to price, right? Price elasticity. By the way, so the actual estimation is a little more complicated than this simple equation. In practice, we use more data, more complicated models and techniques, but just as an example, I'm considering the simplest possible case. And another important example from economics is the Keynesian consumption function. In the Keynesian macroeconomics, the consumption C is understood as a function of income. So household consumption increases as the income increases, but not one-to-one. So household does not consume all the income. Some are saved, and or sometimes household need to borrow money to consume more. So we have the same structure. Consumption is determined by like income as a function of income, but there are parameters and errors. The parameter beta 1 in particular means that it's the consumption amount of consumption that does not depend on income. So even if you do not have any income, still you have to consume this much. So we call this autonomous consumption. You have to spend like minimum amount of say food or like rent or the basic things. And on the other hand, beta 1 is called the marginal propensity to consume. So if you make like one more dollar, then how much would you save out of that? Like I would say, for example, I would save 20 cents and 80 cents will be consumed, for example. Then my marginal propensity to consume is 0.8. And if you were good at macroeconomics, this beta 1 marginal propensity to consume was an important parameter to measure the effect of government spending. So the effect of government spending depends on something related to this. We call that multiplier effect. So if you remember, look up the textbook, macroeconomics textbook, and then this is also estimated using some kind of regression model. Of course, more advanced techniques, but basic idea is from this linear regression model. Okay, so as you see, a lot of examples fit into the linear regression model. So we have, of course, there are general terminology about the model. So we put those names. Y is called dependent variable. Dependent variable because it is determined by other variables. So it depends on the other variables. And X is called independent variable, or I prefer, like different textbooks use different names. X can be also called as the explanatory variable because X is the variable that explains Y, right? So I like that term better, even though but as opposed to dependent variable, people call X as the independent variable. but I may call it explanatory variable. And beta 0 is called intercept or constant term. This is from mathematics. It's a mathematical term. And beta 1 is the slope or coefficient, also from mathematics. And epsilon is the error term or disturbance term or noise, means the same thing. So, by the way, when I use subscript I, this denotes the observation. So we have 12 observations by month. So I runs from 1 to 12. So I captures the one of the random samples, right? And as I said earlier, our goal is to predict the value of y, the dependent variable, using x. We would like to explain how y changes or how y is determined using x. And then coming back to the scatter plot, as a result of the linear regression, it will be a linear function, right? Beta 0 and beta 1 will give you a trend line that looks like this straight line, right? And then you can put their names. So when x is 0, the starting point is beta 1, the intercept. This is the intercept, which is beta 0, or fixed cost. Even if you do not produce anything, still you have to spend this much cost. And the slope is when x increases by, output increases by 1 unit, cost increase by beta 1. So that is the slope. So beta and slope determines the shape of the trend function, trend line. The trend line is determined by those two parameters. As you know, as beta 0 changes, it will move parallel. It will be parallel shift. And if beta 1 changes, it will become flatter or steeper. So the slope is determined by beta 1. And then the difference between the trend line and the observations are epsilon, the errors, right? So so at this point, when you produce 1 unit, your cost realization of your cost is lower than the true or the underlying cost function. So there may be a negative error. I don't know why. It is just an error, accounting error or inventory problem or measurement error, whatever. I don't know. You found some money out of a vault, whatever. I don't know. They are errors, so they are not explained. So that's epsilons. Okay, this is the structure. And then so far we learned parameters are beta 0 and beta 1, and data are pairs of x and y's, right? And we assume that we observe n number of pairs of x and y, cost and output cost, and other examples, consumption income or price and quantity, and you can think about many examples. And what we want to do is we would like to estimate the parameters. And the parameters are usually denoted as, the estimators, we estimate the parameters. So the estimators are denoted as beta 0 hat and beta 1 hat. We put hat on top of that parameter. Then it means estimators. And then, as you know, those estimators are calculated from the sample, so it is random, right? So it is known and it is random. And we are going to use Excel. And what we are going to do is, usually in the textbook starts with how to derive the estimators first. How to, it is important. How can we calculate those estimators? That's important, but I'm going the other way. I will demonstrate Excel, and you get some kind of estimators. I don't know how you got it, just Excel calculated that for you. And I will first show you what we can do using those outcomes, those estimators. If you have estimators, I'll show you many things you can do, and then later I will explain how those estimators are calculated. I think that's a better way to explain and easier to understand the how the mechanism of this estimator. By the way, the name of the estimator is the ordinary least squares estimation, which will be explained later, right? So you don't need to know it right now. And I'm going to show you how to do it on Excel. So this is the data, the same data I showed you in the slides. So there are 12 observations on output and another 12 observations on the cost, output, and like of course it's a really simple data. In practice, you are going to have much more observations or many more like variables. I'll just show you. First, click data, and in the last chapter, we installed data analysis toolpack, right? You have to install this add-on. It's in chapter 11 Excel demonstration, and then if you click this, you takes time. You have regression here. This is what we are going to use. Click here, then you have to put y, x. I'm going to include y range. Y is cost. Y is the variable to be explained that is determined by other variables. And x range is this. We will explain cost using output. So output is x, and label, the first line is label, and you do not need to do anything. I will just go OK. Then you get excuse me, you get table with a lot of numbers. The goal of this class is to explain the meaning of many of those numbers. My goal is to explain I don't know, maybe all of these guys. By the way, it's familiar. Coefficients, standard error, t-statistic, p-value, lower 95% confidence limit, upper 95% confidence limit, and same thing, 95%, repeat it again. That's not necessary. So, and here R square, which is important later, standard error, observations. So these are what we are going to learn throughout this chapter, and this is the basis. And the first thing you have to look at is these numbers. Look at these numbers, because this is the estimator. So from our data, the intercept is estimated to be 8.188995215. I will explain how it is calculated later. And the marginal cost, by the way, the intercept is the fixed cost, and the marginal cost is estimated to be 2.3877512. So these are the estimation results. Let me simplify to like this, right? So I will show you what we can do using those numbers. And again, this is the same result copied from Excel, and I will explain what's what, and then clear out those tables. Okay, I am going to explain three things. First, we will study the statistical properties about the estimated slope, right? So we will consider confidence interval hypothesis testing, right? It is so we will study statistical properties first, and second, we will use the results to predict y. Maybe this is more practical application of the results. And finally, we will study the errors. So there are unexplained parts which are considered simply random errors, but we will study how good our estimation is and how much we can explain the variable, something like that. So from the errors, amount of the errors, there may be some potential analysis. So we will look at the error in the third step. So in the next video, I will start the first step, which is a simple application of the previous chapter's results. Okay, see you there.